Hi, I'm Garrison. I want to be very thorough with this review, maybe more thorough than you're going to need, but who knows, it'll probably be helpful to someone. So I want to start with the concept review and then we'll get into the actual practice problems and whatnot. Hopefully you remember the average rate of change formula. It's just change in y over change in x, or if you're dealing with the function f, it is change in f over change in x. So now let me write that. I'm going to make a cheat sheet as we go here. So that'll be our first thing, is that average rate of change on some interval a, b is just change in f, or whatever function you're dealing with, change in y, change in g, whatever, over your change in x, which is going to be, in this case, b minus a, because that's what we're calling our endpoints of the interval that we're concerned with. And average rate of change is helpful if you want to talk about the average speed that an object has, right? Speed is just change in position over change in time. So you can talk about, if I drop this marker, right, what was the average speed that it fell with from up here to down here, right? So I could do position here minus position here, divided by how long it took to fall that amount. That's great and all. But sometimes you're going to want a more precise number, especially with physicsy related stuff. It's kind of why calculus became a thing, was to do physics, or at least that's one of the reasons. You're going to want something more exact than an average rate of change. You're going to want an instantaneous rate of change. For instance, what is the marker's velocity there? Right in the middle of the fall, or whatever. So how are we going to find that? Well, let's say if I were to graph the position versus time of that marker as it fell, I would probably get something like this, where it starts at the top of my hand and then it ends at the lower hand. If I wanted to find the exact velocity of that marker, right in the middle, so here, rather than the average rate of change of this function over the whole interval, right, which would be the slope of this graph, I want the slope just right there. So how am I going to do that? Because obviously I need 2 points in order to find the slope over any interval. Well, I could always just, for example, look at my slope, between here and, I smudged it, between here and here, right? And that would give me a better idea of the velocity of the marker just right there. And of course, I could look at smaller intervals. If I zoomed in really far, just around that point, the graph would practically be a straight line. And I could find the slope, here's the point I'm interested in. I could find the slope right here and right here, the slope there. And it would be just barely off, but it would be incredibly close to the velocity of the marker just at that one point in time. That's the idea behind a derivative. So, to formalize that and to make sure that we have absolutely no error, we're going to take the limit as my 2 points, my interval that I'm looking at gets smaller and smaller and smaller around whatever value I'm looking for. So if this is time t that I'm looking at, and down here is a time, t plus a little bit, plus some small change in time. If that change in time is really small, I basically have the velocity just at that instant, because the interval I'm looking at is so small that it's basically an instant. So, to formalize that, I would say that the velocity of the marker as it falls is equal to its y value a little after, t plus delta t, minus its y value at the time I'm interested in, t, divided by, right, that's just change of position, divided by how much time it took to fall that amount. Okay, now that should look super familiar because that's just average rate of change. Here's the trick. With the derivative, we want just at it, the tiniest little interval of time, just at that little instant we want the slope. So I'm going to take the limit as the interval I'm looking at, approaches a width of 0. That would be the velocity at just that instant. And of course, if I wanted to extend this to not just physics, then I would say instead that the derivative is what we call an instantaneous rate of change. The derivative of any function f, which you're going to call, you can call it various things. You can call it f prime of x. You can call it df dx. You can call it d on dx, like that, of f of x. It's all the same thing, it just means instantaneous rate of change. That is going to be equal to f at x plus delta x, which is just like whatever x value I'm interested in, but slightly later, minus f of x over delta x, so the average rate of change over that interval, in the limit as the width of that interval goes to 0. Instantaneous rate of change. That's the second thing I'm going to put on this cheat sheet. Couple things to note. Sometimes instead of delta x, you're going to see people write h. That's just because h is quicker to write than delta x. The point is, it's just some number that's going to 0 that represents the width of the interval we're looking at. Doesn't matter what the actual symbol is. One other thing, this is called the Lagrange notation for a derivative because this is how Lagrange wrote it. And this, my personal favorite, is called the Leibniz notation for the derivative. The reason it's my favorite is because it's a very nice visual representation, like in just a couple symbols, of what a derivative is. Because you know how I could write, average rate of change as delta f over delta x? The only difference between average rate of change and instantaneous rate of change is the interval, the delta x that we're looking at, is incredibly tiny. And that's what this dx means. The d instead of the delta just implies that there is a tiny, tiny, tiny change. So tiny, tiny, tiny change in f over tiny, tiny, tiny change in x. That's essentially what a derivative is. That's why I like Leibniz's notation. Okay, I've swapped out our sort of physics example for a more general, just mathematical example. And I want to talk about the other way that you could find the derivative. This is more, it doesn't have to be, but usually you're going to see it used for finding the derivative at a specific x value. So here I'm just going to call whatever x value we're looking at, I'm going to call that a. Same exact deal as with this. It's the same idea. It's just that now we're doing it at a specific x value. So instead of x plus delta x, I'm just going to have x. And then instead of f of x, I'm going to have f of a. And then on the bottom, instead of delta x, I'm going to have x minus a. Again, it's just average rate of change. And its average rate of change over that tiny, tiny little interval where basically the graph is a straight line. So the slope is really well approximated by an average rate of change. So the average rate of change over this interval. Okay, and then same deal, instead of average rate of change, obviously I want instantaneous rate of change. So I'm going to turn this into that by saying, okay, well, let's have x go to a so that our interval ends up being incredibly tiny, right? Like as I get, x moves here, and then x moves here, and then x moves here, and then x moves here, until the interval we're looking at is like, it basically can't get any smaller. Then take the slope. So that would be our slope at a particular point a. So that's going to be, the way you write that is f prime of a in Lagrange's notation. If you wanted to write this in Leibniz's notation, it's a little funky, and you're not going to see it a whole lot, but it'd be df dx, and then you do this bar, and at the bottom you write x equals a. Essentially the same thing, just here it's at a particular x value, here it's more general. One simple example, the derivative of x squared with respect to x. With respect to x just means that x is the variable that we care about. X is the thing that is changing, that we are analyzing the change in x squared over. Okay, the derivative of x squared with respect to x. That is the average rate of change over some interval delta x, but then in the limit as the width of that interval basically becomes infinitesimal. Okay, so if I expand that out, I get x squared plus 2x delta x plus delta x squared minus x squared over delta x. So then clearly these x squareds cancel each other out, and I'm left with just 2x delta x plus delta x squared over delta x. Well, I can cancel a delta x from the top and bottom, and I'm left with, ooh, I forgot to write my limit. Be very careful, that will get points off on a test. Limit is delta x approaches 0 that. Okay, delta x is canceled, and I'm left with the limit as delta x goes to 0 of 2x plus delta x, which is clearly just 2x. So if my f of x is x squared, then my f prime of x will be 2x. And then specifically at x equals 2, my slope will be 2 times, of course, 2, which is 4. Let's do this over with this definition to make sure we get the same thing. So f prime of 2 equals the limit as our x approaches 2 of whatever our x is squared minus 2 squared over x minus 2. Again, just average rate of change, but then as our interval gets really, really small. That's x squared. Oh, I almost forgot my limit again. That's the limit as x approaches 2 of x squared of minus 4 over x minus 2. X squared minus 4 is the difference of squares, so I'm going to rewrite that as x plus 2 times x minus 2. Clearly these x minus 2's cancel, and I'm just left with 2 plus 2, which is 4. Same thing. I'm going to leave this on here for now. One other definition to have is a tangent line and a normal line. A tangent line is just the line that hits the graph at a certain point, and it has the slope of the graph at whatever point it hits. Okay, so in this case, you know, if this is x equals a, then it's going to hit the graph at a comma f of a, and it's going to have a slope of f prime of a. That's all that means. And then a normal line is just this, but instead of being having the slope, it's going to be like perpendicular to the slope. So a normal line would look like, I'm going to draw through my writing here, but a normal line would look like that. And so it would still hit a comma f of a, but it would have a slope of, remember, if it's perpendicular to another line, then its slope will be the opposite of the reciprocal of that line. So this guy will have a slope of negative 1 over f prime of a. So then if I wrote the equation for the tangent line in point slope form, I would have, my point is a comma f of a, my slope is f prime of a, so it's going to be y minus f of a equals f prime of a times x minus a. It's just the line that has a slope that is equal to the derivative at that point and also hits that point. And then the normal line is just the one that's perpendicular to that. So normal line, same point, but opposite and reciprocal of the slope. One other thing to be careful of is that you can't always take the derivative of a function. Like, for example, here's the graph of the absolute value of x. What is the slope? I drew this badly, but that's supposed to be at the origin. What is the slope at 0, 0? So what is f prime of 0? If I look at it coming this way, it should be negative 1. But if I look at it coming this way, the slope is just 1. So the derivative here actually does not exist. It is undefined. The terminology we use for that is that at 0, f of x equals the absolute value of x is not differentiable, right? Anytime I'm taking the derivative, it's called differentiation. So it's not differentiable if I can't take the derivative. So at x equals a, f of x is not going to be differentiable if, and I'm going to write the whole limit thing that we have up here, but just remember, conceptually, if the slope is not the same from the left as it is from the right, then the derivative does not exist. Okay, again, this just means derivative when we look at it from the left does not equal derivative when we look at it from the right. That means it's not differentiable. Fun fact, if f is differentiable, what we would need for that, or at least part of what we would need for f to be differentiable, is clearly we would need to be able to plug in at that point, and we would need to be able to approach the same point from the left and from the right, right? Otherwise our derivative certainly will not exist. Well, hey, if we can plug in at a point and we can also approach that point from the left and from the right, that's just the definition of continuity. So if f is differentiable, then it must be continuous. F is differentiable implies, that's what the arrow means, implies f is continuous. The reason I left this on the board was to show that derivatives, if you're trying to do it like from first principles, as in like this limit, derivatives can be pretty nasty. Luckily, you have learned quite a few tricks that will allow you to basically shortcut this whole process and just immediately know that the derivative of this function is whatever. Some of the most basic ones are, and these are pretty intuitive, are that if I have a constant, which I'm going to call c for constant, then the derivative of that constant with respect to x, or with respect to anything really, is just 0, right? Because it's just a number. It doesn't care what x is, it's always that number. It's not changing. Its rate of change is 0. Secondly, if I have a constant times a function, then clearly the function is just going to be, c times taller than it would be without being multiplied by that constant. So what that means is that the slope is just going to be c times steeper, which means that the slope is going to be c times the slope if we didn't multiply by that number, okay? In practice, this just means if I'm differentiating something and it's multiplied by a number, I can just sort of keep the number off to the side, differentiate the rest of it, and then put the number back at the end. And lastly, if I'm differentiating two functions and they're being added or subtracted from each other, I can just go term by term, differentiate that guy, then differentiate that guy, okay? I don't have to differentiate them like together or anything funky like that. It's also very easy to see this if I go back to the limit definition. The limit definition of the derivative, that is. Because I can just split the limit into two separate limits that are being added or subtracted from each other. And what I just showed you, where you evaluate the derivative from this of a function, you can do that for basically all of the formulas I'm about to show you. That would be way too much to fit into one video, so I'm not going to do it, even though I'd like to. But trust me when I say that, for example, the derivative of e to the x, we know is that. And that limit, you can evaluate it. It's on the internet. There's plenty of resources for this kind of thing on the internet. That limit actually just works out to be e to the x. Okay? So the derivative of e to the x with respect to x is just e to the x. That's why e is so cool, is because it has this property. It's kind of goated, actually. You could do a similar process to show that the derivative of natural log of x with respect to x is 1 over x. Again, there's plenty of stuff about this out on the internet. I just don't have time to show you all of these proofs. Also, I don't want to overwhelm you. Having said that I don't want to overwhelm you, though, I am now going to write down like 8 more formulas because you're going to need a lot. There's a lot on this test. This one's called power rule because it's the derivative of x raised to a power with respect to x. I'm just calling that power n. It can be whatever number you want. If I take the derivative of x to the n, I'm going to get n times x to the number that is 1 less than n. You can think about this, like to remember it, you can think about this as you take the exponent, you move it out front, turn it into a coefficient, and then you drop the exponent down by 1. So like we saw earlier that the derivative of x squared with respect to x is 2x. You can get that result from this as well. Exponent comes out front, and then you raise it to the power of number that is 1 less than the exponent. So 2 minus 1 in this case is 1. So the derivative of x squared is 2x. The slope at any point on the graph of x squared is going to be equal to 2 times the x value of that point. If I have two functions that are multiplying each other and I want to take the derivative of that whole thing, you can use product rule, which basically says take one of them and differentiate it, and then just leave the other one. Then add and differentiate the other one and leave the first one. We'll work through plenty of examples. So naturally, after product rule comes quotient rule, where if instead of two functions multiplying each other, I have two functions dividing each other, that. I'm sure Gable told you the story about the whole ho-de-hi thing, and I definitely do not use that to help me remember that one. Okay, we're on the home stretch now. 6 more, but they're all sort of grouped into one big category here, trig derivatives. This first one's kind of nice. Derivative of sine is just cosine. This next one kind of is not as nice because it's counterintuitive. Would be nice if the derivative of cosine was sine, but it's not, it's negative sine. And then these other 4, I don't know what to tell you, man. One other thing, these derivatives are only going to be this if x is in radians. If it's in degrees, you're going to get a different answer and you're going to end up writing the wrong thing on the test. Always, always, always in radians for calculating. That's everything. Now, like I said, these don't have to just be things that you memorize. Like, there are proofs out there. However, realistically, you're going to want to also memorize these. And I also understand that, like, not everyone wants to prove every single one of these formulas, so I'm sorry. It is what it is. Just make sure that you know what they mean, and it shouldn't be too big of an issue that you're just having to memorize them. Okay, that being said, I just want to do a bunch of examples now. I'm going to do like a solid 2/3 of your study guide unless I end up cutting part of this out. And I've made a couple of my own just for fun. Not just for fun, actually. I think it's going to be helpful. So, number 3, the derivative of 2x squared plus 3x minus 1 with respect to x from the limit definition of the derivative. So that's going to be the limit as delta x approaches 0 of that function evaluated at x plus delta x minus the function at just x. Don't forget to distribute the negative. This becomes a plus, minus, minus, all over the change in x. And of course, we're evaluating the limit as that change in x becomes basically nothing. Okay, so I gotta expand this all out now. Like so. Okay, so I have a 2x and a minus 2x squared. Sorry, 2x squared and minus 2x squared. I have a 3x and a negative 3x. Those are gonna go away. I have minus 1 and a plus 1. And the rest of this stuff has a delta x in it, all divided by delta x. So I can go ahead and cancel a delta x from each of those. And of course, cancel the delta x on the bottom as well. And I end up with this, which of course, if I now finally am able to plug in 0 for delta x, I'm just gonna get 2x plus 3. And you can verify that that is not what you're supposed to get. Okay, it's because this should be 4x. So then this is 4x plus delta x plus 3. Plug in 0 for delta x. There we go. Okay, 4x plus 3. 4x plus 3. Okay, number 5 now. This is just straight differentiation practice. If f of x equals 4 minus 1 over 2x squared. Then let's find the derivative of that f prime of x, the derivative of that with respect to x. Now I know from here that if I have two things being added or subtracted, I can just differentiate those guys individually. And I know also that the derivative of a constant is 0. So the derivative of 4 is going to be 0. Let me write that actually just to be clear. Okay, the derivative of 4, that's just 0. So I just need to worry about -1 times the derivative of 1 over 2x squared. Now, using my exponent rules, I know that if I have an exponent in the bottom, I can make that a negative exponent in the top. So I'm going to rewrite this as negative derivative of 1/2 x to the -2. Okay, and I know, first of all, that if I have a constant multiplying it, it's just going to come along, so I don't really need to worry about it. I just need to worry about differentiating x to the -2. And I know that if I have x to the power of any number, then I just need to bring that power out front and then raise it to the power of 1 less than that. So let's do that. I'm going to get -1 times, and again, the 1/2 just stays. Okay, and then the -2 comes out front. And then we drop the power down by 1. So -2 minus 1, -3. Okay, and then I have a negative and a negative, those cancel. I have a 2 and a 1/2, those cancel. So I just get x to the -3, which again, using my exponent rules if I want to, I can rewrite that as 1 over x cubed. Okay, number 6, kind of the same deal. I want to find the derivative of g of x, which is this stuff. So I want to find the derivative with respect to x of 3 root x minus 6 over x squared plus 5 times pi cubed. And if I go term by term here, 5 pi cubed looks weird, but it's just a constant, okay? It's not going to change if x changes. So the derivative of 5 pi cubed, because again, I can go term by term, just 0. And so I just have to worry about the derivatives of these guys. Now again, if I have a constant multiplying a function, I don't actually need to worry about the constant. I can just sort of put it off to the side. So that's actually what I'm going to do here. I'm going to rewrite this as 3 times, and then I'll just worry about differentiating the square root of x. Okay? And then minus, and again, I have a 6 here. It's just going to come along. So 6 times the derivative of 1 over x squared. And then these are both just going to be power rule. Remember, if I have the square root of something, that's just that thing to the power of a half. And if I have 1 over x squared, I can flip it and then make the exponent negative. So x to the -2. Okay, so then we're just going to need our power rule. Take the 1/2, bring it out in front. Take the exponent, subtract 1 from it. So 1/2 minus 1, -1/2. And then over here, same deal. Pull out a -2, put that in the front, drop the exponent down by 1, -2 minus 1 is -3. So then simplifying a bit, I can drop this back down, make it 1 over the square root of x. And I can make this x to the -3, 1 over x cubed. And there's my final answer. Okay, number 9, kind of the same deal, but we're gonna need a new thing. Can't just use product rule, or can't just use power rule for this one. We want the derivative of this function, so we want d prime of t. In this case, the function is in terms of t, not in x. So instead of d on dx, I'm gonna write d on dt. And then I'm taking the derivative of that. I have a constant here. I know that that constant can just come along. It just can sort of sit on the sidelines while I differentiate the main thing. And I'm going to go ahead and write this square root as t to the 1/2. Now I know how to differentiate this and I know how to differentiate this, but they're multiplying each other, which means I'm going to need product rule. Like I said earlier, the way product rule works is you take one, you differentiate it, you just multiply it by the original of the other one. Then you add, you keep the first one, you differentiate the other one. So here, I'm going to go ahead and differentiate my t to the 1/2. So the 1/2 comes out in front. 1/2 minus 1 is -1/2. And then the natural log of t just stays. And then I'm going to add, I'm going to keep my t to the 1/2 the same, and this time I'm going to differentiate natural log of t, which is just 1 over t. Okay, and then just cleaning up a bit, I can distribute this 3, and I can drop this down into the bottom and turn it back into a square root like that. Distribute the 3 to this term as well. Also notice that this is t to the first in the bottom, this is t to the 1/2 in the top, so I can cancel the t to the 1/2 in the top from the bottom. So I'm going to have 3 over t to the 1/2, which is 3 over the square root of t. And there we go. Okay, for number 10, same sort of deal, but now we're using some trig derivatives. Okay, again, I can just go term by term here, so that's what I'm going to do. And in this term, I can pull out a 4 and just like let it sit on the sidelines. Like so. Now, we know that if I have 1 over something, I can do that thing to the negative exponent. So here I have 1 over x to the first, which is going to be x to the negative 1. And secant is just secant. So when I differentiate my x to the negative first, negative 1 comes out front. And I subtract 1 from the exponent, so I get negative 2. And then I'm subtracting the derivative of secant x, which secant x times tangent x. So dropping my negative 2 back down into, or my negative 2 power that is, back down into the denominator, I get negative 4 over x squared minus secant x tangent x. Okay, number 11, I can't really do much with that as far as manipulating things to make it easier as to like what am I differentiating or what am I not. But I do see that I'm having one function divided by another function, and I'm differentiating that. So I know that this is probably what I'm going to want. So I have the bottom times the derivative of the top. Now the derivative of 2 is just 0. And then we're doing minus the derivative of x. The derivative of a linear function is just going to be the slope of that thing. So the derivative of x will just be 1. So my derivative of 2 minus x is just negative 1. Another way of looking at it, if I'm trying to differentiate negative x, I know that I can pull out a negative 1. And I know that x is, of course, x to the first. So I can actually use my power rule here. Pull out the 1, drop the exponent down, so I get negative 1 times x to the 0. Anything to the 0 is just 1, so altogether I get just negative 1. Okay, so bottom times the derivative of the top minus the top times the derivative of the bottom. Oh, I smudged it. Again, derivative of the bottom, same deal. Derivative of 2 is 0, don't have to worry about that. Derivative of x is 1, either by this reasoning or by just, it's a linear function, slope of 1. And then in the bottom, I need the square of my, my denominator. And then simplifying things, I get negative 4 over x plus 2 squared. Okay, number 12, I want the tangent line to negative 2x cubed plus 3x. That's my function. And I want the tangent line to that function at x equals negative 1. So obviously, if I'm writing the equation of a line, I need a point and I need a slope. And I know that a tangent line has the slope of the function at the point it hits. And I know that it's going to hit at x equals negative 1. So that's the x value of my point. I have like half a point, but I need the y value of that. So I'm going to plug in negative 1 to figure out what the y value is at x equals negative 1. Which is negative 1. So my point is going to be negative 1, negative 1. Okay, I have a point, I need slope. What is the slope? Well, of course, it's just the derivative of the tangent, or of the function at x equals negative 1. I'm pulling out my coefficients and separating my terms. That's the same as negative 2, derivative of x cubed, plus 3, derivative of x. Power rule now, that's negative 2 times 3 times x to the 3 minus 1, which is 2. Derivative of x is just 1, and I'm multiplying that by 3. So my derivative at any x value is negative 6x squared plus 3. But I don't want it anywhere. I want specifically the slope of the function at x equals -1. So that's what I'm going to plug in. Okay, so there's my slope. There's my point. Putting it all together, y minus y1, which is going to be y plus 1, because it's a double negative. Y plus 1 equals slope times x minus x1, which again, double negative. I'm going to end up with plus 1. That is my tangent line to that function at x equals -1. If I graph that function, I'm going to do this off the dome, so it's going to probably not totally be right. But it's going to look something like that, and maybe we're right there. So if I graphed it, the tangent line would hit that function right there, and also have the slope of that function at that point. Okay, 15. F prime of 0, or f of x, is that. Obviously, we need f prime of x first, so we'll go term by term here. 3 can just stay. The derivative of sine of x is cosine of x. And then minus, and the 2 can just stay. The derivative of e to the x is just e to the x. Alright, there's my f prime of x. Now I need f prime of 0. That's 3 times cosine of 0. Remember your unit circle, cosine of 0 is 1. And then minus 2, e to the 0 is going to be 3 minus 2 equals 1. Okay, number 16. This one's a calculator question, actually, so let me show you how you would plug in on your calculator to get a derivative. That should be under menu, and then go down to calculus. And for me, it's number 2 because I have a CAS. It might be 1 for you, I'm not sure. But derivative at a point. Variable x, value is what? 7, and we want the first derivative. I don't know if you know what that is yet, but don't worry about it if you don't. So x equals 7, and then I just have to tell it what my function is. And when I press enter, I get a nasty number. When I press control enter, I get like 260.32-ish. And you're always going to want 3 digits. You can truncate or round. I'll just truncate here. So my calculator says f prime of 7 is about 260.323. This one is f differentiable at 2, and then this is our function. F is a piecewise. This is just a line, this is just a quadratic, so we shouldn't have to worry about differentiability, you know, having the same slope from the left as we do from the right at any point other than x equals 2, really, because x equals 2 is where it stops being a quadratic and starts being a linear. So we might have this weird disconnect where it looks like that or something, in which case the slope here is going to be like something positive. But if I look at it from the left, coming from the right, the slope is going to be something negative. In that case, it wouldn't be differentiable. But that's what we need to check here is the slope coming from the left, in other words, basically just the slope right before x equals 2, so the slope of this function, is that slope equal to the slope coming from the right, so the slope of that function, at x equals 2. Okay, so it is the derivative of that guy, which is, again, just go term by term here. Derivative of 3x should just be 3. Derivative of 3x squared, bring the 2 out front. So I get 6x to the first, so minus 6x. And derivative of 5 is just 0. That's the derivative of the function before x equals 2. After x equals 2, everywhere to the right of x equals 2, the derivative of that function is the derivative of 7 minus 9x, which is just this term, the derivative is 0. This term, the derivative is just -9. So we need to make sure that if I plug in x equals 2, this equals that. So let's see, plug in x equals 2 here, and I get 3 minus 12, which is -9. And obviously these two are the same thing. So then, yes, we are differentiable at x equals 2. As a bonus, let me graph this and show you what it looks like. Yeah, look at that. Look how smooth of a transition that is. Last problem from your study guide that I wanted to talk about is number 20. It's asking if f of x is this, what values of this a and this b are going to make f of x differentiable at x equals 4. So again, same sort of deal. We need the derivative from the left at x equals 4 to be the derivative from the right at x equals 4. Clearly the derivative coming from the left will be the derivative of this guy, because to the left of x equals 4, that is what f of x is. And from the right, the derivative will be the derivative of this guy, because to the right of x equals 4, that's what f of x is. So let's see here. The derivative with respect to x of a root x plus bx squared minus 1. Don't get tripped up by the fact that we have letters instead of numbers here. They're still just constants. So we can just sort of keep them off to the side. Again, square root of x equals x to the 1/2. So the derivative of a root x is a times 1/2 comes out front, and then 1/2 minus 1 is negative 1/2. Derivative of bx squared, again, the b just comes along, it's a constant. The 2 comes out front, and then we subtract 1 from the power, so we just get x to the first. And the derivative of negative 1 is 0. So coming from the left, our derivative will be a over 2 root x plus 2bx. All right, coming from the right, our derivative will be the derivative of this, which again, the 16 can just come out front. 1 over x is just x to the negative first. So the derivative of 16 over x is going to be 16 times, bring the negative 1 out in front. Then negative 1 minus 1 is negative 2. And then the derivative of bx is just going to be b. So that's negative 16 over x squared plus b. So I need this and this to equal each other at x equals 4. So let me plug in. I want a over 2 squared equals 2 plus 2b plus 4 equals 16 over 4 squared plus 2 plus a 4 plus 4 16 equals and I'll go ahead and solve for a just for kicks. A equals negative 4 minus 28b. That, believe it or not, is your final answer. I think you're used to, especially from last unit, all of these things where you have a system of equations where you have to figure out exact values of a and b. But here, we've already used all the information we have, that this and this should have equal derivatives at x equals 4. And this was the result we got. So really there's a whole range of values of a and b that will make this function derivative as long as we, or differentiable, I mean, as long as we have that this is satisfied. Whatever a is, it's equal to negative 4 minus 28 times whatever b is. Okay, that's everything from your study guide. I have like a couple extra that I want to go over real quick, because I think that these would be helpful to make sure you have on the test. Here's the first one. Had you been shown this last unit, you would have just cried. It is the limit as as a approaches 0 of x plus a squared sine of x plus a minus x squared sine of x over a. Luckily, now we can look at this and go, oh, hey, you know what this looks like? So this is just the derivative with respect to x of x squared sine of x. How am I going to do that derivative? Well, I have a thing that I can differentiate times another thing that I know how to differentiate, so I'm probably going to need product rule. So let's go ahead and differentiate just x squared. 2 comes out in front. 2 minus 1 is 1, so I just have 2x. And then I just leave the sine of x. Just leave it alone. Then I add, now I leave the x squared alone, and this time I differentiate my sine of x, which is the derivative of sine of x is cosine of x. So in like 30 seconds, you have just evaluated a limit that would have like broken you last unit. Okay, 2 more. Here's a table, and I want us to estimate f prime of 3.5, given just this table. We know that a derivative is, you take a function, you look at an interval, you say, what is the average rate of change over that interval? And then you zoom way, way, way in until you're looking at like the world's tiniest interval, and you say, what is the average rate of change over that interval? And it's basically just the average rate of change at one point, or at least in the immediate, infinitely small vicinity of that point, right? So if I take this function, and I look at the smallest interval I can, and I say, what is the average rate of change of that interval? And that interval is sort of centered around or really close to x equals 3.5, then I'm probably going to get a pretty good guess as to what f prime of 3.5 might be. So that's what I'm going to do. I'm going to pick the smallest interval I can that is right around 3.5. In this case, it's going to be 3, 4. And I'm going to find the average rate of change there, because it'll be pretty close to the instantaneous rate of change right in the middle there. Okay, average rate of change on 3, 4 is, let's see, f of 4, which is 24, minus f of 3, which is 6, over 4 minus 3, which is 1. So all told, I get 18. So I have that 18 is kind of approximately equal to f prime of 3.5. These sorts of questions, especially, are just to make sure that you understand, like, what does a derivative do? Okay, one more, and that is the limit as x goes to 3 of this sine of x over the square root of x minus sine of 3 over the square root of 3 over x minus 3. We want to compute that limit, and we want to do it without hating ourselves at the end of it. So how are we going to do that? Well, we can look and we can say, hey, this looks an awful lot like that, which means that this must be the derivative of that function at x equals 3. So it's the derivative of, and I'm going to bust out my cool looking Leibniz notation, because heck yeah. But if this was, let's say I let f of x equal sine of x over the square root of x, then obviously this would also be f prime of 3. Okay, anyway, I basically just need the derivative of that now. So f prime of x, I'm going to take advantage of the fact that I just labeled this f of x. F prime of x equals, and this one's going to be a quotient rule. Bottom times the derivative of the top, so square root of x times derivative of the top is cosine of x, minus the top sine of x, times the derivative of the bottom. Again, the square root of x is x to the 1/2. So derivative of that, the 1/2 comes out front, and then you raise it to the power of 1/2 minus 1, which is negative 1/2, all over the square root of x squared, which is just x. Okay, so all that's left is then to plug in 3. So I'll do that up here, continue my original line here. So this is the square root of 3 times cosine of 3 minus sine of 3 times 1 over 2 root 3. Again, I'm using my exponent rules to just drop that down into the denominator. All over 3. It's not the nicest looking answer ever, but it is the answer. So I'm going to put it in a box. Okay, that's it. That's all I have. Make sure that you know all of the stuff that is over here, because that is almost definitely going to be something you are tested on. And if it's not something you're tested on, you will be expected to know these things like all of the rest of the year and all of the rest of the math classes you ever take. So make sure you know them. Make sure you know also like what a derivative is and why this is a thing. If you're interested, of course, I can never stop encouraging that you look up proofs for these things. I do think that they help with your understanding. They kind of force you to think for yourself. They help you to see how it's all connected and all of that. Obviously, it's like overachieving, but I like it, so maybe someone else will too. As always, hfamualphatheta.com to like and subscribe, I guess. Yeah, ask for help if you need it. We got tutors, we got math teachers, you know, you got the internet at your fingertips. The digital age is amazing. I'm gonna turn off the camera now.